Alright, so in this video we're going to start talking about Lagrange multipliers. And essentially what Lagrange multipliers are is there are quantities that allows to find the optimum values of a function of several variables. So I'm just going to write this down here. Multiplier. It is essentially some quantity that we usually denote by the letter lambda. And the way it works is given some function f of several variables, so usually we have function of 2 or 3 variables, so we can have f of x, y, z. That's our main function. That's the one we want to optimize. And then we have a constraint. So the constraint, as you know, from single variable calculus must also be a function. So the constraint is going to be a function that is going to have a specific form, and this is going to tell us exactly within which boundaries do we want to optimize that particular function. And this function could be anything. In a physical sense, it could be something like the volume of some shape or the surface area of some particular thing that we're manufacturing, or it can even be a function itself that represents something like the sales volume of a particular company or a business. So there are many different applications of this, and it really depends on the way that you want to utilize the concepts of multivariable calculus to model your particular system. But in general, what we have is we have two functions. We have the function that we need to optimize. This is the function that we need to solve for. And then we have the constraint function, which we call g. And now what we're going to do in order to solve these two things is we're going to set up an equation. So nabla f equals to lambda, which is the Lagrange multiplier. This is going to be a single value that is going to be the same for all values of these two vector quantities, because remember that the gradient of a scalar function or a scalar field, as we have discussed about what these functions are in the past, is the gradient function, which is denoted by nabla, which is essentially just a vector that takes the partial derivatives with respect to each of the variables involved in the function. Essentially what this is this is going to become a vector function. So for nabla f, what we're going to have is partial derivative with respect to x, and I'm going to use the shorthand notation here, partial derivative of y with respect to f, and then with respect to z. So this is just the same, and the same applies for g. So in the end, what we're going to end up having as our equation is going to be this g and then zg. And now remember, it doesn't really matter whether the constraint function contains all these variables. It could be something that is confined to a lower dimensional space, but in general we want to set up an equation that is like this, and this should allow us to solve for different values. And in general, it's good to have constraints that basically involve all the same variables as f, because we want to have an equal number of functions or an equal number of equations as we have variables, so we can solve for them. So what can you notice about this particular system? Clearly we have 3 unknowns because we want to find the optimum values, which means that we want to solve for x, y, and z. And obviously we're going to have this value, unknown value, which is the Lagrange multiplier, so that's a 4th value. So how many equations do we have here? Well, these equations make up 3, but we have 4 unknowns. So where's the 4th equation? Well, the 4th equation is going to be the constraint itself. So equation number 4 is going to be the constraint. That way, by solving these equations and then plugging them back into the 4th equation, we can actually solve for these values. And in general, there are many methods to doing this. This just involves some algebraic manipulation. But I'll show you one of the easiest methods and the one that I like to use the most. And in order to do that, I'm just going to show you an example of how this works. So let's clear the screen here. So let's have the following problem. Let's have a box of unknown dimensions. So let's call this x, this length y, and this length z. So z is just the height of the box. It's going to be a solid box. So we want to maximize the volume So maximize the volume. So that means find those values x, y, and z, which are the dimensions of the box that will maximize the volume, subject to the constraint that the surface area must be equal to 60 centimeters squared. And remember, when we have a constraint, it can either be equal, less, greater than, or there are a whole bunch of things that come into play. But in this case, we just want it to be equal to 60 centimeters squared. So what we're going to do with this is we're going to set up two functions. So the first function that we want to optimize is obviously the volume. So we're going to have a volume function here. And because this is just a box, we know it's just going to be the product of all lengths. So that's going to be the function we want to optimize. And then our constraint function is going to be this. So the surface area, that means that the sum of all these little areas, we have 6 faces on this box. So that means that we're going to have x times y, that's the bottom face, and the top face. And then we have yz is this face, and then xz is this face. So obviously we need to multiply all of those by 2. So 2 times xy plus 2 times yz plus 2 times xz is equals to 60. And because this is the constraint function, we can actually simplify this to the best form. So this is going to be the easiest form to work with. We just divide everything by 2. And that's going to give us 30 centimeters squared. So what are we going to do with this? Well, essentially what we do is we call our function, our constraint function g. We're going to make it equal to the value of the constraint. So that means that the function itself is just going to be defined by this portion here. So we're going to make, and this is what we do all the time, we set the function, because this is the constraint, right? We set it equal to the constant here, the constant value, and then that means that the function is defined by this expression here. So what we're going to do now is we're going to find the equation that looks like this. So we're going to have to take partial derivatives for both functions, and in this case we don't have f, we call it v. So to avoid confusion, I'm just going to call it v. So that's our gradient for that function of volume. So let's set it up. Let's have our nabla v that's going to be equal to the following. So we set up our vector, and then the first element is obviously going to be the partial derivative with respect to x. So if we look at here, partial derivative with respect to x, that's going to be yz. Then partial derivative with respect to y, that's xz, and then partial derivative with respect to z is going to be xy. And then this is going to be equal to lambda. And now we're going to have the partial derivative of g, which is this whole expression here with respect to x. That's going to be y plus z. Then partial derivative with respect to y, that's going to be x plus z. And then finally, partial derivative with respect to z, that's going to be x plus y. So now we have our 3 equations. And our 4th equation is just going to be this equation itself. So what we're going to do now is we're going to grab these 3 equations and we're going to set it up in the following way. So remember, when you have a vector multiplied by a constant, the constant just basically multiplies every single element in it. So what I like to do in order to solve these problems is to set up lambda such that it is equal to fractional expressions. So in this case, we're going to have for the first row, we're going to have yz equals to y plus z, because this is the same as setting up the equation yz equals to lambda y plus z. And all I'm doing is I'm dividing both sides by this, and then I'm just solving for lambda. So that's what we're doing here. For all 3 equations, we're going to solve for lambda. So for the second equation, we're going to have lambda. So I'm just going to set it up in a row. So you're going to see that that's going to turn out very nice. And we're going to have xz over x plus z. And then the last one is going to be xy over x plus y. And hopefully you can see where I'm going with this here. So now that we have these three equations in line, what we can do is we can grab any two. So I'm going to grab this two here. And I'm going to try to solve for, to reduce the amount of unknowns or variables involved. So I'm going to cross multiply this times that and this times that to get rid of those denominators. So I'm going to have x, y, z, once I expand this product, plus yz squared equals to x, y, z once again here, and then that's plus xz squared. And then these two are going to cancel out. And now we're left with yz squared equals to xz squared. So obviously, we know that for a box, we cannot have zero height. Obviously, it also makes sense in this problem to have any of the lengths equal to 0. So we know that we can cancel that out. And that means that y should be equal to x according to this particular equation. So that's a really nice thing because we just now reduce the number of unknowns. We can go ahead and try to solve for this. So what's the next thing we can do? Well, we can solve for this this final expression here. Now that we know that both are equal, we can write x squared over 2x, which is the same as x over 2. And now we know that our lambda, or Lagrange multiplier for this example, is actually going to be equal to x on 2. Now that's one of the things we can do, but the whole idea behind setting up all three equations in linear form like this, so in a whole row, is so that we don't actually have to directly calculate lambda. We can just use it as a dummy variable so that we find the other values of the unknowns that we're actually interested in. So in doing this, we don't actually need to solve for lambda at all. I mean, we could obviously calculate it once we know what the value of x is. But the whole point of this is to reduce the amount of steps that we need to follow. And in doing so, we just eliminate the need for calculating lambda directly. So now we calculate this, we can plug this into another equation and then see what we get. So now let's take this expression equals to this expression and see what we get from that. So let's see what we get from that. So we just found y equals to x, and now our second expression was going to go down again, xz over x plus z. And we already said that this is equal to x on 2, right? Because we just reduced, we just substituted for y equals to x into this one, and that gave us x on 2. So this one is going to be a lot easier to solve. So we're going to have cross multiply again. That's going to give us 2xz equals to x times x plus z. So that's going to be x squared plus xz. And then subtract that from the other side. That's xz equals to x squared. And now we can divide by that side. So that means that z is going to be equal to x. And that's a really interesting thing because that means that all of these variables now are going to be equal. And that's just a coincidence. That's just depends on the problem and the constraint that was given to us. But don't expect this to be the case for other problems. Now we know this, we can plug these values back into the constraint equation, which was xy plus xz plus yz equals to 30. So what I'm going to do is I'm going to replace everything by x. So this is going to be x squared plus x squared again equals to 30. And this is going to lead us to x squared, so that's 3x squared equals to 30. So x squared equals to 10, and then x equals to the square root of 10, which is approximately, let me just calculate it here very quickly. That's about 3.162 centimeters. So that's going to be the length. And that means that all of these are also going to be around that length. Now, what's our Lagrange multiplier? Well, we said that it was equal to x on 2, so we know that this is going to be around 10 on 2, or it's going to be around 1.581 centimeters. Actually, that's dimensionless. Remember, this is just a parameter, so it's dimensionless. But this is just to give you an idea. And you know that we didn't actually need to calculate this by using this method of setting up the equations in this in a single row like this. So now that we have that, we can proceed and calculate what's the maximum volume that we can have given these dimensions and given this constraint for the surface area. So we had that our volume was x, y, z, so that means that we're just going to have this value to the power 3. So let's have this value to the power 3. And this is going to be roughly 31.62 centimeters cubed. So that's the maximum volume that we can have given that our surface area is 60 centimeters squared. And we have a box. So the box has to have all these lengths that are perpendicular to each other. And that's basically what we're going to have. This is going to be our final answer. And I apologize for this rather messy setup here, but there were a lot of things involved that I wanted to go through. And optimization using Lagrange multiplier, it goes beyond just these physical problems that we can mess with and play around with. It actually applies to finding maximum and minimum values of a function, and just in the same way that we would use the second derivative test that we have already learned how to use with partial derivatives, we can use Lagrange multipliers to do that, and that's what we will be doing in the next video.